Hi, my name is Mark. I am one of the maths lecturers at New College Durham. Today I want to give you a little bit of a taste of what A-Level maths is like by talking through the idea of trigonometry and talk how trigonometry changes from GCSE to A-Level as we start to look at the topic in a bit more depth. So we're going to start with thinking about what we should know so far, and this is generally the idea of SOHCAHTOA. When most people are introduced to the idea of trigonometry, it is through the concept of right-angled triangles. So if I draw myself a nice right-angled triangle, I label the specific angle theta. I can label three sides of this triangle because I have the hypotenuse, which is the side that is opposite the right angle, and also the longest side of the triangle. I have the opposite, which shockingly is opposite the labelled angle that I have, and I have the adjacent, which is the side that is next to that angle. Now from there I can create essentially three different ratios. These ratios are sine theta, they are cos theta, and they are tan theta. Sine theta is the opposite over the hypotenuse, cos theta is the adjacent over the hypotenuse, and tan theta is the opposite over the adjacent. Well, what actually are these? They are literally just ratios. If I have two triangles, one which has a 5 on the hypotenuse, 4 on the opposite, or a different triangle that has 8 on the opposite and 10 on the hypotenuse, they have the same sine theta ratio because 4 over 5 is the same as 8 over 10. Fundamentally what it means is they have the same angle, they are similar triangles. So all sine theta, cos theta, tan theta are, when we look at them like this, are essentially ratios. Now we can develop this and start to look at things like the sine rule and the cosine rule when we look at triangles. And this allows us to develop this rule for things beyond right-angled triangles. Now this comes up a bit in A-Level as well. We also look at concepts such as area of the triangle as well. But there is another area of trigonometry that we should have been introduced to as well. And this is where things get a bit interesting. We may have also met this. Now this is a graph of theta against sine theta. And I have 1 and -1 as my maximum and minimum values respectively. I have 180 degrees as an intercept on the x-axis and 360 degrees as another root to this function. Now this actually continues forever and ever and ever. It also goes off in the negative direction as well, forever and ever and ever and ever and ever. There is also a graph of cos theta. There is also a graph of tan theta. I'm just going to draw the cosine theta graph here between 0 and 360. So I've got 1, I've got -1, and again, I've got roots at 90 degrees, roots at 270 degrees, maximum back up at 360. Now, by the power of magic, here is a graph of tan for 0 to 360 degrees. Some differences: there is no maximum and minimum value. We also have undefined regions of our graph represented by a dotted line. We will be talking a little bit about those in a bit. Technically, these are referred to as asymptotes. These are just essentially points where the graph does not exist. So this generates a question. How can something both be about the ratios of sides in a right-angled triangle, but also be a representation of an infinite wave? There's a dichotomy between those two concepts. They don't match up. So how do we get them to match up? That's what A-Level is all about. We can't just sit things in boxes anymore. Things can't just be because. There has to be a reason, and that reason is something called the unit circle. So the unit circle is a circle with a radius of 1. In our prior learning, we should have met the formula for the equation of a circle with centre at the origin, which is x squared plus y squared is equal to r squared, where r is my radius. Now what this does is, in this situation, therefore, gives us an equation of this circle as x squared plus y squared equals 1, because 1 squared is just 1. Now, all x and y are essentially any coordinate that exists on this circle. Every single coordinate on this circle can be represented through that equation. Now, when we look at this, and we look at this equation, x squared plus y squared equals r squared. Something squared plus something squared equals something squared. Where have we met this before? Well, this is a squared equals b squared plus c squared. It is essentially just Pythagoras theorem. And if we pull this information out of my diagram, so radius, if I go down and across, I've got the x coordinate, I've got the y coordinate. What actually happens is I can pull a triangle out of this circle. It will have a radius, which in this case is 1. It will have x as the horizontal component and y as the vertical component along the corridor up the stairs, essentially. We can then label our angle theta, and essentially what we have at this point is a standard right-angled triangle problem. And we can use our ratios of trigonometry. So sine theta is opposite over our hypotenuse, so opposite is y, hypotenuse is 1. So we get that sine theta is equal to y. So it means y is equal to sine theta. Can do the same with the adjacent and the hypotenuse. Cos theta is adjacent, which is x over hypotenuse. So we can say that cos theta is equal to x. So we get x is equal to cos theta. So now we have a right angle triangle with one side being cos theta, one side being sine theta, one being 1. Now, x and y are any point on this circle. At the minute, I have this right angle triangle drawn like so. However, there is nothing stopping me from drawing a right angle triangle that exists on this circle in this other quadrant here. Again, I will have a radius. Again, I will have a coordinate, x and y. However, when I look at these coordinates, this time my x is in the negative quadrant, y is in the positive quadrant. But we've got to remember, x is cos theta. So as I move around my circle, so as I start to move my point around the circle, cos theta, which is represented by x, will become negative. And then I can keep this moving around again. So I can move into my next quadrant and create another radius. And again, this time, I'm still going to have a negative x value, but I will have a negative y value. But again, remember, x is cos theta, y is sine theta. So at this point, when I've rotated all the way around, so more than 180 degrees, but less than 270 degrees down here, then I'm in a situation where both x and y are negative. But remember, x and y are cosine theta and sine theta. So both cosine theta and sine theta will be negative. I can then keep going again. And I keep going round and round and round and round and round. And in the next quadrant, so between 270 degrees and 360 degrees, I am back to a positive x, but a negative y. Now what we're going to do is tabulate this information. So between 0 and 90, we have a situation where the x is positive and the y is positive. But remember, x is cos theta, y is sine theta. Between 90 and 180, we have a negative cosine, or a negative x, and a positive sine through the positive y. Between 180 and 270, both of these are negative. And between 270 and 360, cosine is positive, but sine is negative. We then have some specific values labelled 0, 90, 180 and 270. Well, if we think of an angle of 0, if I have an angle of 0, I will have essentially a perfectly horizontal line. When I draw a perfectly horizontal line on this, my x-coordinate will therefore be 1, because that is the radius of the circle, and because there is therefore no height, my y is 0. At 90, I have a vertical line, which means there is no x component, which is 0, and y will therefore be 1. Get to 180, it is a horizontal line, but in the other direction, so I get a -1 for my coordinate, and again 0 for sine value, and then at 270, it is 0 on the horizontal and -1 on the vertical, your y coordinate or sine value. So what we're going to do is take this table and we're going to look at this with the graphs of sine and cosine from before. What we can see here is essentially our tables match up with our graph. Let's look at the graph of cosine. So we begin at 1, it's then in the positive region until we get to 90 degrees, at which point it hits 0, then goes into the negative region, it goes down to -1 at 180 degrees, works its way back up to 270, and then is in the positive region until we get to 360. Sine, you can follow it round, the exact same thing happens where the table matches up with the graph. Now we go, well, why is this infinite? Well, this is infinite because once you do a full turn at 360 degrees, you are back at your starting point. You can keep going, and again, and again, and again, and again. So this means our graphs could go on infinitely in that positive direction. So why do they go infinitely negative? Well, simple. You just turn in the opposite direction. So if you go the opposite way, with sine, we would end up in the negative quadrant, and that will match with what happens on our unit circle. So it means you essentially get this infinite wave in both directions. But what about tan? So we've got sine and we've got cosine. Well, when we think about tan, we're going to go back to the triangle that we created from our unit circle. We said that x was cos theta, and we said that y was sine theta. Now, if we think about our general trigonometric ratio for tan theta is my opposite over the adjacent. So taking this information, I can say that tan theta is equal to sine theta over cosine theta. Now, tan theta did lots of strange things, and you ended up with an asymptote in your graph at 2 occasions between 0 and 360. And you were told that theta cannot be equal to 90, and theta cannot be equal to 270. Again, you may know that fact, but really what we've got to be thinking about is why. Well, that comes from this. Tan theta is sine theta over cos theta. This means tan of 90 is sine of 90 over cos of 90. Well, sine of 90 is 1. Cos of 90 is 0. We can't divide by 0. It is undefined. We get an error if we try to do it in a calculator because the answer is undefinable. So this is why the graph ceases to exist at that point. That is why a graph of tan theta looks the way it does. Same at 270. Cos theta is 0. We are going to get an error again. So this was just a quick little taster of kind of how things go within A-level maths, how we have to start thinking about the world of mathematics and trying to make links between things that we may not have necessarily made links about before. This is nowhere near exhaustive even for this small little area. I haven't even got talking about how we can tie this together with the idea of gradients of a line and tan theta, talking about Pythagoras in a bit more depth with relates to this. There is huge amount of scopes and avenues still to go within this topic, but it is just exciting. We're starting to look at maths that you know and link it together or tweak it or think about why certain things happen. Now, for those of you interested in maths, and also those of you who are interested in further maths as well, where does trigonometry come within the specifications? Now, trigonometry is its own unique topic area within the A-level maths pure content. However, it is also embedded within 4 other areas of the course. So within the differentiation, the integration, numerical methods and vectors, you will have elements of trigonometry embedded within there. The trigonometry topic on its own is about 4 weeks worth of teaching across those 2 years. It is incredibly substantial. It is what we refer to as one of the key 4 topics, along with differentiation, integration and exponentials and logarithms of the A-level qualification. It also crops up within mechanics, kinematics, forces and Newton laws, and moments. All involve significant trigonometric work, particularly by the time you get to the 2nd year of the mechanics qualification. Further maths, trigonometry is embedded within 8 of the 9 topics that make up the core qualification content. So complex numbers, polar coordinates, hyperbolic functions, vectors, matrices. Trigonometry is really rife in those topics, so a good working knowledge is vital, but also this ability to think about trigonometry in a very different way and develop your understanding of the topic will really be expected within further maths. It's also featured heavily in the 2nd year of material with regards further mechanics. So further mechanics, it doesn't really come in year 1, but in year 2 of that material, trigonometry is embedded quite heavily. Thank you very much for your time. If you have any other questions about maths or further maths, please just get in contact with me. My email address is here. It could be about calculators, equipment, or anything about any specific topics or things like that. I've also put together some materials to aid with the transition between GCSE and A-level, perfect for this time with the abrupt end to year 11 and waiting for next academic year to start. Any questions about those materials, please feel free to get in touch with me and I'm happy to help with those areas.